Hello, this lecture will cover page 221 in my lecture notes, so please print that page out and have it in front of you as I present this lecture on Synchronous Logic Design, Part C, the Stepper Motor Controller. If you look on page 221 of your lecture notes, we talk about design number 4. Using the design procedure on page 210 of your lecture notes, I want you to design the stepper controller. It's nothing more than a synchronous counter for a simple stepper motor using JK flip-flops. So on page 210, we had a synchronous logic design procedure, and I'm going to show you practically how to use this on a stepper motor controller. Before we start, I want to talk about a stepper motor for a minute. And generally, when you think of a motor, you think of a shaft that's rotating very, very fast, a lot of RPMs per minute in a continuous 360-degree direction. But stepper motors are different. Stepper motors are a lot slower. They move in incremental steps in one direction or another, and they're slow compared to a conventional motor. If you read with me in your textbook, this is on page either 418. If you have the newer textbook, it's on page 452. If you have a newer edition, it's on another page, but basically this is where we're going to be here. Let's get it here so you can see it. It's this right here, the stepper motor controller. If you read with me, we will now apply this design procedure that I've been talking about on page 210, lecture note page 210, to a practical situation, driving a stepper motor. A stepper motor is a motor that rotates in steps, typically 15 degrees per step, rather than a continuous motion. Magnetic coils or windings within the motor must be energized and de-energized in a specific sequence in order to produce this stepping action. Digital signals are normally used to control the current in each of the stepper motor's coils. Stepper motors are used extensively in situations where precise precision control is needed, such as in positioning of read-write heads on magnetic disks, in controlling print heads in printers, and in robotics. What I'd like you to do is stop the video and read the rest of this page and the next page, and we're going to design the stepper motor control. If you take a look, what I have done here is I've taken this block diagram here, basically of the stepper motor control, which is a synchronous counter, and it uses two flip-flops. Now, this is a very simple diagram. In actuality, a stepper motor is going to have 128 states, maybe 256 states, with a lot more coils to get these incremental 15-degree steps. But here, our simple stepper motor is going to give us 90-degree steps. 490-degree steps. So, but you'll understand the concept here as we go through it. Notice it looks like we have 4 outputs here of the synchronous counter, and we do, but it's because we're using the bar output to energize other coils as this motor rotates clockwise or counterclockwise. So we just use 2 flip-flops. They give you the transition diagrams here at the bottom of the page, or on the page you're looking at, which looks like this. But what I've done is I combined these two to look like this. I want you to notice how to read this. First of all, when the asynchronous input signal direction equals 0, that is a clockwise motion of that stepper motor. And the sequence is the states, the binary representations of states 3, 2, 0, 1. 3, when the clock edge comes, if d equals 0, it goes to 2. If the clock edge comes, d equals 0, it goes to 0, or to state, binary state 1, and back to 3. If the asynchronous input signal d equals 1, no matter which state you're in, let's say you're in 2, it's going to count binary 2, 3, 1, 0, 2, 3, 1, and 0. And asynchronously, whenever that direction signal changes, no matter which state it's in, it's going to continue to count. If the direction signal goes to a 0, it's going to count clockwise, and the direct asynchronous D input 1, it goes to a 1, it's going to sequence, rather. It's going to rotate counterclockwise. So if you go through this synchronous design procedure we talked about, we're going to go through each one of these steps, and practically we're going to use this in an application to design this stepper motor control. Now, all this is prefaced on you reading these 3 or 4 paragraphs here. And what we're going to do is we're going to proceed. Once you get this, remember I told you, once you get this state transition diagram, the hard work's done. It's all procedural to go through to finish the circuit, to realize the circuit. But getting this transition diagram is your first step, and it's a very important step. They give that to you at this point for this very simple stepper motor controller. So if you take a look, we're going to look at the present state to next state table. Now, they have this in the book right here. And you could surely look in the book. And what I want you to realize here is that they use a flip-flop B and a flip-flop A, where A's being the least significant bit. You have to be careful with this. I don't care if you use a B and an A or a Q sub 1 or Q sub 0. I used a Q sub 1 and a Q sub 0 being the least significant bit. Here's your present states. Here's your next states. So my flip-flop inputs aren't JB, KB, and JA, KA. They're going to be J1, K1, J0, K0. But I want you to notice I'm doing something a little different starting in this design. In our synchronous logic design procedure, what we're going to do, instead of having those present state to next state maps, we've been using present state to next state maps. And if you take a look at them, they look like this. You remember this? When we constructed these maps here that look like this, where we had a slash through each midterm, we're going to cease to do these next state maps, and we're going to incorporate them in our present state to next state tables. And it's going to make this a little bit easier for you. So if you take a look, they did this up here, but I made this a little bit bigger in your notes. You might have to write this in. What I've done is I added my asynchronous input, my directional input, which just forms a third bit here. And generally, you can put it on this side, you can put it over here. It's just how you lay out your 3 variable K maps here. So I have 3 inputs, D, and then my flip-flops, Q1, Q0. And that's going to give us 8 possible states, and I list them. And notice we're just looking at if the direction input is 0, if you have to be looking the whole time here, you have to be looking at your state transition diagram, because you build the present state to next state tables off of the state transition diagram. So if you notice here, if we're in state 0, 0, 0, and the direction input is 0, what's the next state we go to? So you go back here and you look. When you're in state 0 and the directional input is 0, you go to state 0, 1. So you put that in your map. You put that in your table. You go to 0, 1. And what if you're in state 0, 1 and the directional input is 0? If you're in state 0, 1 and the directional input is 0, you go to state 1, 1. And you go back here and you'll see that. You go to state 1, 1. And you go through each one of these very carefully. Notice the first 4, D equals 0. The last 4, D equals 1. And you get to your next state. And then what I'm going to do, and what I want you to do to start doing in the rest of your designs, is putting in your control inputs as part of your present state to next state table. It's going to alleviate these next state maps down here. You won't have to do these next state maps because they're part of the present state to next state table. Now, what do I mean by that? Well, then you take a look up here and you use your excitation table to do this. If your Q1 is at a 1, Q1 is at a 0, and you stay at 0, J's a 0, and K has to be a don't care. J's a 0, K has to be a don't care. If your Q1 is a 0, in the next state it goes to a 1, J is a 1, K is a don't care. If Q1 is a 1, in the next state it goes to a 0, J's a don't care, K's a 1. And if Q1 is a 1, and the next state it stays at a 1, J's a don't care, and K's a 0. And you take your time and you fill this in. Now, I want you to go ahead and put these headings in if you don't have it in your notes. And I want you to do this last one. Very carefully go through and see if you get the same result I do. Once you get this present state to next state table complete, and it includes your control inputs, you can go straight to your final output maps. And that's what we've done. If you take a look in the book, or you can take a look here, keeping in mind here that in the book they use this flip-flop B and flip-flop A, and what I did is I used flip-flop Q1 and flip-flop Q0. Don't know if I explained that, but notice that I wrote instead of JB KB, it's J1 K1 instead of JA KA as the inputs for the least significant bit flip-flop. I use a J0 K0. I wrote them up here. The book uses A and B flip-flops, and I use flip-flop 0 and flip-flop 1. But if you go through and you form your output expressions, and I did that for you, I want you to notice here that for the final output maps for flip-flop Q1, I simply just go to my present state to next state table for the states that I need, and I put in the corresponding values. Notice that notice that some of the states are not used, so they're don't cares. When some of the states aren't used, they become don't cares. But I build my final output maps, and I'm building those final output maps from this present state to next state table information. With this being state 0, 1, 2, 3, 0, 1, 2, 3. Notice though that I'm looking at state 0, 1, 2, 3, but here, because direction inputs 1, it's state 4, 5, 6, and 7. That's all the possibilities here. And when I have the don't cares, I fill in as I go through here. Notice that I can form my output expression for J1 using K-maps, which is D0 Q sub 0 bar, or D bar Q sub 0, which is the exclusive OR of asynchronous input D and Q0. My K1 turns out to be, using K-map reduction, D Q0 or D bar Q0 bar. That's simply the exclusive NOR of D and Q0. If I go to my final output maps for Q0, notice I get J0 being equal to the exclusive NOR of D and Q1, and K0 being the exclusive OR of D and Q1. Now, you could build it. You could build these using the additional gates here, but why not just use an exclusive OR gate or exclusive NOR gate? And that's what I'm showing you here. So, finally, you realize the circuit. And depending on what textbook you're using, you just take and build that particular circuit. And this is that circuit right here. Notice I have my clock, very slow running clock that's going to provide the steps. I mean, this provides the arrows that motion you. Don't forget that these clock edges provide these motions here to the different states, which are basically rotating that stepper motor incrementally. But here's my inputs for JB and KB. Don't forget that's J1, K1, and JAKA, which is J0, K0. I built those inputs from my expressions. My outputs B, Q1 if you will, and Q1 bar, and A, Q0 and Q0 bar go to those current amplifiers to provide enough current for the coils in the motor. This particular circuit will rotate that stepper motor in 90-degree increments. Not very granular, but you can see how we used the synchronous logic design procedure to design this synchronous controller. In this case, the stepper motor controller. The only difference is in our present state to next state table. We're going to start including these control inputs. And if you include the control inputs and you make it part of the table, you can go straight. I mean, the procedure is pretty easy. You determine the number of states you need. That determines your number of flip-flops. And then you have your state transition diagram. You get that from the specification. And from the state transition diagram, you have to account for every arrow. And you do that in your present state to next state table, incorporating those control inputs, which are your J and K terms. And then you simply go from this table now to your final output maps. Realize the circuit and you're done. That concludes the lecture.